Hello friends, welcome to part 3 of Electricity and Magnetism paper solution of Guwahati University 2022 physics honors. Right, so we have already solved question number 1 and question number 2 in part 1 and part 2. Links are given in the description box. So in part 3 we're going to solve question number 3, right? And before we start, please subscribe the channel, because being a YouTuber we also need motivation to work hard for you, right? uh, if you don't subscribe, actually this thing is very disappointing for us, to make a half an hour video. To make a half an hour video we need at least 2 hours, right? So that's why please subscribe the channel, okay? So it really inspires us to create new contents for you. And please do share and hit the thumbs up button also, and please stay connected. Subscribe to channel, also hit the bell icon so that you get notified when new video will be uploaded. So now let's start. So here is the question number 3a. Two infinite parallel plates carry equal but opposite uniform charge densities plus and minus sigma. Find the electric field in between the two plates and also outside the two plates. Suppose these are the two plates. One is positively charged with charge density is positive sigma. This is negative plate, right? Negative sigma. This is plate 1. This is plate 2, right? So let me take that way. And so we are to find, suppose let us take 3 points, 2 outside the plates and 1 between the plate, that is Q. Suppose this is R and P are outside the plates, so we are to calculate the electric field between the two plates, that means at Q, and also outside the plate, that means at P and R, right? We know that here is the answer. Okay, we know that electric field due to any infinite sheet of charge density sigma is given by E. So I am writing the magnitude only, so let me use black here. E is equal to sigma by 2 epsilon naught, right? Sigma by 2 epsilon naught, right? So therefore let us calculate first the electric field due to this positive plate, right? That means plate 1, right? So due to plate 1, electric field E is given by, so let me write E1, that's going to be given by sigma 2 sigma by 2 epsilon naught. Similarly, due to the plate 2, right? Due to the plate 2, second plate, the electric field, that is E2, so E2 will be minus sigma 2 epsilon naught. So here you see the direction of E1 should be away from this positively charged plate, because electric field due to a positive charge, that should be away from the positive charge, and the electric field due to this negatively charged plate, it should be towards the negative charge. So this is the direction of E2, right? They are opposite in direction. So now therefore net electric field at P. Electric field outside the plates. Outside the plate. At P, that will be what? That will be given by E net. That means resultant electric field. That's gonna be E1 plus E2. If you use these two values here, then you will get sigma 2 epsilon naught minus sigma 2 epsilon naught. That's gonna be equal to 0. This is the electric field outside the parallel plates, right? So now let us calculate the electric field between the two plates, right? Now electric field between the two plates, right? Let me electric field between the two plates or two sheets at Q, suppose. That's gonna be given by E1 and E2. Both are equal to sigma 2 epsilon naught, because here you see this electric field due to this first plate, as it is positively charged, that should be away from the plate, right? And due to electric field due to the negatively charged plate, that should be towards the negative plate. So here you can see the direction of both E1 and E2 between the plates is same. So in both cases E1 and E2 will be sigma by twice epsilon naught. So here therefore net electric field or resultant electric field between the two sheets E net, that will be equal to E1 plus E2 is equal to sigma 2 epsilon naught plus sigma 2 epsilon naught, and that's gonna be 2 into sigma 2 epsilon naught, 2 gone, so we have got sigma by epsilon naught. So that is the electric field between the two plates, right? So hope you have understood this. So here is the next question. Derive Poisson's equation from this. Write Laplace equation, and we have to write these two equations in Cartesian coordinate system, right? We know that electric field, so let me write electric field is negative gradient of potential. Right, so that is E is minus grade V. Here V represents potential. Number 1, let it be equation number 1. According to Gauss law, divergence of electric field is rho by E. Here rho represents, let me take this one as equation number 2, and this rho represents charge per unit volume. Charge per unit volume. So you can write like this: charge per unit volume, right? Now let us use equation number 1 in 2. Using 1 in 2, then what are we gonna get? So we have got E is equal to minus grade V, so let us put this here. So then what we gonna get? Del dot minus del V is equal to E by epsilon naught, right? So it implies del square, that is Laplacian operator, minus rho epsilon naught, rho by epsilon naught, right? So here I have missed the V here, so that's BV, sorry. Right, so this equation is called Poisson's equation. So let me go to the next slide. So here del square, this is Laplacian operator. Right, this is the Poisson's equation in Cartesian form. Right, this same equation can be also written as like this. So let me copy this and just, so this is the Poisson's equation we have got. This is the Poisson equation minus, right, that is what we have got. So it also can be written as second order partial derivative with respect to x of v plus second order partial derivative of v with respect to y. Similarly, this, it also can be written this way, right? So this is the this was the Poisson's equation. This can be written in this way or in this way. So let me take, this is equation number 3. Now let us write the Laplace equation. So now you see, if the volume charge density is 0, if rho is equal to 0, then equation number 3 implies equal to 0, or you can write in this form. So this is your Laplace equation, right, in Cartesian form. So hope you have understood this. Now let's move on to next question. So here is the next question. So that the electric field inside a charged hollow sphere is 0, right? Suppose we have a charged hollow sphere. Suppose this is a sphere and it is uniformly charged, right, and it is hollow. That means inside the sphere it is empty, right? The interior of the sphere is empty and it is uniformly charged with the amount of charge q, right? And its radius is, suppose, r. This is its radius, r, capital R. So let us take a point P inside the sphere, that is point P, right? So let me write here. We are to show electric field at a point P inside a hollow sphere, inside a hollow sphere of radius r, that is capital R, with uniformly charged distribution, with uniformly distributed charged Q positive, and let us assume a Gaussian surface let me write it properly. Gaussian surface through the point P of radius small r. So here small r is obviously less than capital R, right? And this Gaussian surface will be also spherical of radius small r, right? So electric flux through the Gaussian surface, electric flux through the Gaussian surface is phi is equal to electric field E 4 pi r square, that is the area of the Gaussian surface, 4 pi r square. Because here you see we have taken the Gaussian surface is also spherical and its radius is r, and this is the small r is the radius, and the surface area of a sphere is given by 4 pi r square, right? This is the flux. This is number one, suppose. Now electrics, here you see by Gauss theorem, electric flux through a surface enclosing, and that means the statement of Gaussian, according to the statement of Gaussian theorem, Gauss theorem, is that the electric flux through a surface is 1 by epsilon times of the charge enclosed by the surface, right? If a surface enclose Q amount of charge, then the electric flux through this surface will be given by Q by epsilon naught, right? This was the statement of Gauss law. So here you see, here it will be equal to 0, right? Here this one will be equal to 0. Why? Because charge inside the Gaussian surface, charge enclosed by the Gaussian surface. Since charge enclosed by the Gaussian surface, Q is equal to 0, right? This is equal to 0. That is why here we have got phi is equal to 0. So hope you have understood this. Now let us use equation number 1 here. So from equation number 1, this phi can be replaced by u into 4 pi r square. Let me go to the next slide. So here we can write E 4 pi r square, that is equal to 0. Since 4 pi r square is area, so it cannot be equal to 0, right? The only possible value which can be 0, that is E, electric field E. That is what we want to prove, right? So this is the electric field inside a hollow sphere, right? So hope you have understood this. Now let's move on to the next question. So here is the next question. Starting from the electric field intensity due to a point charge, derive the Gauss law in differential form. So here you see, suppose we have a sphere, or let us suppose it is any closed surface, right, and enclose a charge, suppose q. It encloses a charge q, right, and electric field due to, let us consider, so let me write here, let us consider a closed surface enclosing a point source q positive inside it at O. So this is at O, suppose, right? Then electric field intensity due to this due to q positive at p so we have taken a point P on the surface of this this closed surface. We have taken a point P, right, and this part here, as I have drawn like this part is suppose very small surface element ds, right? Okay, we have considered that way. At P on a very small surface element ds, right, the electric field is given by, E is equal to 1 by 4 pi epsilon naught q by r square, right, q by r square. So here r is the distance from the positive charge q to the point P, right? We have assumed that way, right? Now you see, this is suppose equation number 1. Electric flux through the surface element ds is given by d phi is equal to electric field E dot ds, right, and the product of these two will be given by E ds cos theta, right? So where theta is the angle between the electric field, this is electric field vector, and electric field vector, and let me write it properly. This is the electric field vector, and the normal vector that is normal to the surface area element, right? This is suppose n cap unit vector along the along the normal vector to the surface, or you can say the area vector, right? And between these two we have angle theta, right? Okay, now let us assume that the solid angle formed by this area element ds is suppose omega. This angle is suppose omega. So here let me write theta is angle between vector E and n cap, right? N cap, and omega is the I will write it later what is omega. Okay, also let me mention one more thing. This is n cap is unit vector along ds vector. So ds vector is the area element area vector, right, which is perpendicular to the area element, right? Perpendicular to the area element ds, right? Area ds, right? You can say like that. Okay, now what we're going to do, we're going to put the value of E from equation number 1 here. We're going to put that. Then what we will get, d phi is equal to q by 4 pi epsilon naught ds cos theta by r square, right? We can write that way using 1. So just wait, and let me put this one as well. So E vector dot ds, right? Okay, so from where we have got from 1, right? Now you see this solid angle omega is equal to ds cos theta by r square, right? So we can replace that d phi, that is E vector ds vector E vector dot ds vector is equal to q by 4 pi epsilon naught into d omega, right? D omega. So just let me do a correction here. This is this angle is d omega. Suppose let me take d omega, very small angle, solid angle d omega, right? So here what we're gonna write, d omega is the solid angle made by the area element ds at O, right? So at this point at O, this solid angle is being made, right? So now you see how to get the total flux. So total flux through the whole surface, right? Total flux through the whole surface S. So let me write here one more thing. Let us consider a closed surface. Let me mention one more thing of area S. Let me mention this thing here. Okay, so through the surface S, that is phi is equal to integration, surface integration E dot ds. So if you integrate this, then only you will get the total flux through the whole surface, right? Q by 4 pi epsilon naught. This part is constant, so it can be taken out. Integration d omega, right? And integration of d omega is nothing but 4 pi. That means if you integrate the solid angle, for this whole surface, then you will get 4 pi, right? So that means solid angle subtended by the closed surface at the center, that will be 4 pi. Okay, so hope you have understood this. So then what we have got, surface integral E vector dot ds, or yes, so Q 4 pi epsilon naught. So this integration of d omega, that gonna be given by 4 pi, right? So here 4 pi cancel, so we have left with Q by epsilon naught, right? So you can write this one as you can write this surface integral like this as well. You can put here s, right? Surface integral, you can write like this as well. So now you see, if you apply the Gauss divergence theorem, you can write this surface integral in terms of volume integral. So integral V del dot E dot, here it will be dV, sorry, E dV, not dot dV, E dV, you can write that way. And you see, if rho is the volume charge density, or charge per unit volume, charge per unit volume, then you can write Q, instead of Q you can write then you can write Q is equal to volume integral dV into rho, right? So this rho will be given by Q will be given by rho into integration, that means rho into total volume. Total volume will be obtained by integrating the volume element dV, right? If V is the total volume here. So then here you see, del V means it is a very small volume element of this closed surface, right? Very small volume element, you can consider that way, just not like that. So this is the closed surface, suppose you can consider very small volume element, it is not surface, volume element, you can consider that way. So then you can replace this, let me write here, if rho is charge per unit volume, then Q can be written like this. So then here we can write rho by epsilon naught volume integral dV, right? So this implies here we can write this is by Gauss divergence theorem, right? So from this step to this we have obtained by applying this Gauss divergence theorem, right? So here you see volume integral on this left hand side and right hand side both same, so this part must be also equal, right? So that's why we can write del dot E is equal to rho by epsilon naught, and this is the Gauss theorem, differential form of Gauss theorem, right? This is the differential form of Gauss law, you can see, right? So hope you have understood this. So if you want me to continue solving this paper, please subscribe to the channel, because you see, since I have uploaded solution of this paper, Guwahati University BSc Physics Honors paper, so I'm getting views, but compared to number of views, I'm not getting that many subscribers. I know you are watching my videos, please subscribe the channel, because it need each video need at least 2 hours to make the video. Though the length of the video is half an hour, but to make the half an hour video I need to work for 2 hours minimum. So please subscribe the channel and inspire me to create new contents for you, and it will be continued in the next part. So thank you for watching.